You type a prompt into an AI, hit enter, and wait. You sit there watching the cursor blink and the text generate, character by character, hoping the final answer makes sense. Most of the tools we use to catch AI mistakes rely on reading that text, but by the time the system spits out a hallucinated fact or a completely broken line of code, the error has already happened. The damage is done. Researchers are trying a different approach: machine psychology. Instead of waiting for the final text, they peek inside the model's hidden layers at generation step 5, just fractions of a second before it commits to an output, to read its internal cognitive state. If we can read what the machine is feeling right before it speaks, we can catch the early mathematical signs of a hallucination and stop the generation process before a single word ever hits the screen. To test this, a recent study known as Test T08 extracted a 6-dimensional state vector from a language model right at the moment of generation. They wanted to see if they could predict accuracy just by looking at the machine's internal geometry. This chart graphs accuracy against internal state. A calm state achieves 91% factual accuracy. On the far right, a fragmented dissociation state drops to 44% with massive contradictions. In the middle is the overconfidence anomaly. Few contradictions, but error rates near 40%. Researchers call this the hallucination mirage. The model's internal uncertainty collapses too early. It commits to a specific answer path instantly, and that commitment is completely, confidently wrong. These state vectors give us a genuine early warning system. We can predict failure with high reliability before the text exists. We know this works for text. But we need to know if this psychological structure is a quirky byproduct of language models or a universal feature of all artificial neural networks. To find out, researchers designed Test T10. They took this exact psychological framework and attempted to map it onto DeepSeek Prover V2, a massive AI built and trained strictly for formal mathematical theorem proving. Looking at this chart tracking cross-substrate transfer, the top dashed orange line tells the story. At the broadest organizational level, known as a regime, the psychological architecture of the language AI perfectly matched the math AI. Even with entirely different training datasets and end goals, these distinct architectures develop the exact same coarse cognitive scaffolding. While the broad architectures align, zooming into the finer details, what researchers call psychological families, reveals sharp differences in how these distinct models think. The clearest divergence happens when we look at how the models handle the underdetermined state. This occurs when an AI is fed a prompt that is deliberately ambiguous or lacks enough information to solve directly. Graphing fixation across ambiguous prompts, the tall blue bars show the language model panicking, locking attention early to force a guess. Conversely, the math model's shorter orange bars show fixation dropping by 32%. It distributes attention across multiple branches to navigate uncertainty. How an AI handles the unknown is a direct product of its environment. A text generator tries to write its way out by guessing, while a theorem prover maps the logic. They share the same skeleton, but they use it differently. The researchers expanded this framework into entirely new behavioral ecologies, testing code generation AIs and genomic sequence models. The left chart's orange bars confirm this broad regime transfers across every tested system. But on the right, the closure gradient shows finer traits degrade further from natural language, accuracy dropping from 80% in math to 70% in code, down to 50% in genomics. The science is currently mapping visual diffusion models, the AI that generates images. At that architectural boundary, this complex multifamily psychology compresses into a much simpler binary state. This creates a portability hierarchy. We are mapping the convergent evolution of artificial cognition across totally separate digital species. Mapping the mind of a machine carries massive practical value for how we interact with technology. Because we understand this universal architecture, we can build proactive safety protocols that work across almost any AI, checking its mental state in real time. We can engineer automated monitors that watch the internal vectors. The exact millisecond an AI spikes into a dangerous dissociation or overconfident state, the system hits the brakes, aborting the answer before it exists. We no longer have to treat these models as opaque black boxes, crossing our fingers and hoping the final output is safe. By reading the hidden geometry of an AI before it speaks, we take active control of how we predict and trust artificial intelligence.